Welcome to the Bodhi Academy. My name is Amisha Klaso, and in today's video we'll start with chapter 6 of class 11, equilibrium. Now when we talk about equilibrium, it is very important to understand that many of the biological and environmental processes are dependent on chemical equilibrium. For example, if we talk about equilibria involving O2 molecules and the protein hemoglobin play a crucial role in transport and delivery of oxygen from the lungs to the different muscles that are present. Similarly, equilibria involving CO molecules and hemoglobin account for the toxicity of carbon monoxide. So when a liquid evaporates in a closed container, molecules with relatively higher kinetic energy, they tend to escape the liquid surface faster as compared to the ones with lower kinetic energy. Now the number of molecules from the vapor phase, what happens is that they strike the liquid surface and they are retained back into the liquid surface. Now this gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to the liquid form from the vapor. Here we say that the system has reached an equilibrium state. So now here what we are saying is that, say we have a liquid that is in a closed container, okay, and it is evaporating. Say now molecules have a relatively higher kinetic energy. Those are going to tend to escape the liquid state which is present. They are going to escape and they are going to go into the vapor phase. Now some of the vapor phase molecules which are there, they might come and strike the walls in here and there, and they might land back into the liquid phase. So here what is happening, the number of molecules, liquid state molecules which are going into the vapor phase, equally same number of molecules are coming back into the liquid phase from the vapor phase. Here we can say that the system is attaining a equilibrium state. However, this is not static equilibrium, and there is a lot of activity at the boundary between the liquid and the vapor. Here it is not static, as in it is not stationary. After the number becomes equal doesn't mean it won't change further. It will change further because there is more reaction also that is continuing to happen. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation, and it may be represented as H2O, that is liquid, giving H2O vapor. Now the double half arrow here, this half arrow, it indicates that the process is going equally in both the directions. So the mixture of reactants and products in the equilibrium state, that is known as a equilibrium mixture. Now equilibrium, it can be attained in both the processes. We have chemical processes and physical processes. In both the cases, equilibrium can be established. So the reaction may be either fast or slow depending on the conditions that are present, as in the experimental conditions, and how the reactants are reacting with each other, or what is the nature of the reactants. So now say when the reactants in a closed vessel at a particular temperature, they react to give products. The concentration of the reactants keep on decreasing, okay, that is what happens in a reaction. Say two reactants are there, what will happen, they will react together, their concentration will go down, and that will be resulting in the formation of products, and that concentration of products will keep on increasing, while those of products keeps on increasing for some time. Now after that there is no change in concentrations of either the reactants or the products after certain point from whatever reactants are left over. Further, they might not be sufficient enough to convert into the products. Here there is going to be no change that occurs. This stage of the system is called as the dynamic equilibrium, and the rates of the forward and reverse reactions here, they become equal. Now, based on the extent to which reactions proceed to reach to this state of equilibrium, we can classify these into three major groups. First is that the reactions that proceed nearly to completion and only negligible concentration of reactants are left. In some cases, it may not even be possible to detect this experimentally. Now what we are saying is that, say you had certain amount of reactants, okay, maximum amount of whichever could convert has converted into the product. Now there is very negligible amount which is almost like equal to not being there. that much amount it is not sufficient to convert into products. So in these cases, here also we can say there is chemical equilibrium or there is dynamic equilibrium. Why? Because it is almost complete and there is almost like negligible amount of reactants that are left, and this amount is so less that it is sometimes not even possible to be detected experimentally. Next is the reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. Now another case is that what? Wherein the product that is being formed is in very less quantity. Okay, even though reactants are sufficient, yet the product that is being formed is very less. It may be because of the reaction conditions and so on, but here also we can say that the equilibrium stage has attained, yet a less amount of product is formed and the reactants are remaining unchanged. Last is the reaction in which the concentration of reactants and products are comparable when the system is in equilibrium. So here what they are saying, whatever reactants are converting to products, here at one point both of them are equal, the concentrations are equal, such that yet we can say that there is equilibrium that is attained. So now we will talk about the equilibrium that occurs in some of the physical processes. Now physical processes, we know most of the common ones are the phase transformation processes in which one phase is changed to another. So we have three major ones. First is solid liquid, liquid gas and solid gas. First let's look at the solid liquid equilibrium. Now say you have ice and water that is kept in an insulated thermoflask. Okay, insulated thermoflask means there is no exchange of heat that happens between the contents and its surroundings. So whatever is inside does not get affected by the outer surroundings of the flask. At 273 Kelvin and the atmospheric pressure are in equilibrium state, and the system shows a very interesting characteristics. So what we observe is that the mass of ice and water does not change with time and the temperature remains constant. So here what we are seeing is that whatever mass was initially present, mass of ice was initially present and water which was there, it is not changing with time. Okay, over time also nothing is happening, no quantity is being lost over here, nor is the temperature changing. Temperature is also remaining constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. So here what is happening, if you have ice surrounded by water, okay, what we usually tend to happen is that the ice is going to melt down and the molecules of ice are going to go into the water. Here what is happening, because there is no temperature change, because there is no loss of mass of ice that is happening, but it is also not static. The equilibrium is also not static. When I say that, it means that say we have the boundary of the ice, okay, some of the molecules are still going to react with that of the water that is present. Some ice molecules are still going to go into the liquid phase. So this is what is happening here. So the molecules from the liquid water, they collide against the ice and adhere to it, and some molecules of ice escape into the liquid. Some water molecules, some whichever are there, they might come and stick to the ice, whereas some which are already onto the ice, they might slip into the liquid phase. So there is still no change of mass of ice and water, as the rates of transfer of molecules from ice into water and of reverse transfer from water to ice are equal at atmospheric pressure. As much as ice is going into the water, that water is also coming back to the ice. So here we are able to attain a equilibrium. So it is obvious that ice and water are in equilibrium only at particular temperature and pressure. So for any pure substance at atmospheric pressure, the temperature at which the solid and liquid are at equilibrium is called as the normal melting point, or it is also known as the normal freezing point of the system. Now the system here, we are saying it is in dynamic equilibrium, and we can infer this 2 points from here. First is that both the opposing processes occur simultaneously. Opposing processes means the liquid phase molecules are going on to the solid phase molecules, and the solid phase molecules are going into the liquid phase molecules. So both the things are occurring simultaneously. Both the processes occur at the same rate so that the amount of ice and water remains constant. Even the rates at which this process occurs is exactly the same, just so as to maintain the amount of ice that is present and the amount of water that is present. Next we have is the liquid vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U tube with mercury and a manometer. So if you see, this is the U tube, okay, which has mercury, and this is the transparent box. So here we are first adding drying agent like anhydrous calcium chloride, or we can also add phosphorus pentoxide. It is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases. If you see here, first initially when this drying agent was there, what this drying agent does, whatever moisture and all is there, it tends to absorb it. Okay, so here there was basically a equilibrium that was attained. Now what we have done, we have removed this and we have quickly placed a dish full of water. So what is happening, the mercury level on the right side of this manometer is rising up. It will be observed that the mercury level in the right limb of the manometer slowly increases and it finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. So what is happening here is that this adjustment is happening just so as to maintain the constant pressure inside. After some time what we notice is that this quantity of water which is there, this also starts to reduce down. Initially there was no water vapor inside the box. As water evaporated, the pressure in the box increased due to addition of water molecules into the gaseous phase inside the box. So what happened here was, initially because of this drying agent there was no water vapor present. The minute you added this water, the water vaporized over here and that intent increased the pressure inside. So the rate of evaporation remained constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. So whatever vapor was being formed here, due to an increase in the pressure, decrease with time due to condensation, increase in this pressure, it decreases with time. So now because the condensation of vapor into the water is happening, finally it leads to an equilibrium condition when there is no net evaporation that occurs. This implies that the number of water molecules from the gaseous state into the liquid state also increase till the equilibrium is attained. So here we can say that the rate of evaporation will be equal to the rate of condensation. So at equilibrium, the pressure that is exerted by the water molecules at a given temperature, it remains constant and it is called as the equilibrium vapor pressure of water. Higher vapor pressure is more volatile and therefore it will have a lower boiling point. Now from this, three major things that we can conclude is that, first, if you see, the evaporation, it depends on the nature of the liquid, what kind, if you're taking a very volatile liquid or non-volatile liquid, it depends on that also. Second, it depends on the amount of liquid that you're taking. If you take a huge amount of liquid, then evaporation will take time. If you take lesser amount, evaporation will be faster. And also the temperature, if it is a room temperature or if you're increasing the temperature. So these all factors are related to the evaporation. Next, let's talk about the solid vapor equilibrium. Now in this, let us consider the system where solids, they directly sublime to a vapor phase. If we place a solid iodine in a closed vessel, what do we notice is that we can see that the container gets filled with the violet fumes of the iodine, and this intensity of the fumes with time it increases. Now after certain time the intensity will remain constant, there will no longer be any change. At that time we can know that the equilibrium is attained. So hence solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give a solid iodine. Next, let's look into equilibrium involving dissolution of solid or gases in liquid. Now here we are talking about mixtures which are present. So let's talk first about this solid in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature, after which its saturation point is reached, and then further no more amount of sugar or salt is going to get dissolved. If we make a thick sugar syrup solution by dissolving sugar at a higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. So if you try to make a solution of sugar and water, after some time if you stop heating it, the minute the sugar starts to cool down, it also starts to crystallize. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. So the concentration of the solute in a saturated solution, it depends upon the temperature. If the temperature is high, the saturation point will increase. If the temperature is low, the saturation point will reduce. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. So we say have a sugar which is a solution and a sugar solid. So both of them are at equilibrium. Here what we can say that the rate of dissolution of sugar equals to the rate of crystallization of sugar. The more sugar getting dissolved will result to more sugar getting recrystallized. Next, we'll talk about gases in liquids. Now say we have a soda water bottle is open. Okay, some of the carbon dioxide gas, it dissolved in its phases out rapidly. Okay, whatever extra carbon dioxide is there, at times when you open the bottle, the fizz which comes out is because of this carbon dioxide that is being released. This phenomena arises due to difference in solubility of carbon dioxide at different pressures. So there is an equilibrium that is attained between the molecules in the gaseous state and the molecules that are dissolved in the liquid under high pressure. Thus, equilibrium is therefore governed by the Henry's law, which states that the mass of a gas that is dissolved in a given mass of solvent at any temperature is directly proportional to the pressure of the gas above the solvent. So this amount decreases with increase in temperature. So as soon as the bottle is obtained, some of the dissolved carbon dioxide gas, it tends to escape to reach a new equilibrium. So the minute you open it up, it doesn't keep on going up. The minute you open out, whatever is excess is released and then it goes silent. Okay, why? Because here a new equilibrium is attained. After some time, if you close it, reopen it, again that sound will come, but with a lesser intensity. Namely, it's a partial pressure in the atmosphere. This is how the soda water in bottle, when left open to air for some time, turns flat. It can be generalized that. Now, if we have to generalize all of these equilibriums, we can generalize them in this major 4 categories. First, if we talk about solid and liquid equilibrium, we know that it occurs only at one temperature at which both the phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remains constant. Then if we talk about liquid and vapor liquid equilibrium, the vapor pressure is at constant at a given temperature. For dissolution of solid in liquids, the solubility is constant at a given temperature. And for dissolution of gases in liquids, the concentration of gas in liquid, it is directly proportional to the pressure of the gas over the liquid. Next, here we have some general characteristics of equilibria involved in the physical processes. First one is the equilibrium is possible only in a closed system at a given temperature. So for physical properties, we know that first it is only possible. Equilibrium is only attained if it is in a closed system. In an open system, it is not possible. Both the opposing processes occur at the same rate and there is a dynamic but stable condition. So here we said that both the processes, they occur at the same rate. Even in case of the water and ice, we were talking that it was occurring in the same rate. The amount of ice molecules going into the water and the water molecules coming onto the ice, both were equal. All measurable properties of the system remain constant. All the properties which are measurable, they all remain constant. When equilibrium is attained for physical processes, it is characterized by constant value of one of its parameters at a given temperature. The magnitude of such quantities at any stage indicates the extent to which the physical process can proceed because it is reaching equilibrium. Next, we will look at quickly about equilibrium in chemical processes, that is a dynamic equilibrium. Now, analogous to the physical system, chemical reactions, they also tend to have a state of equilibrium. These reactions can occur both in forward as well as in backward direction. When the rates of the forward and the reverse reactions, they become equal, the concentration of the reactants and the product remains constant. This is the stage of chemical equilibrium. So, the equilibrium is dynamic in nature as it consists of a forward reaction in which the reactants give products and the reverse in which the products also give back the original reactants. For a better comprehension, let us consider a general case with a reversible reaction. So, if we have A, B giving us C and D, this C and D can also be reversed back to give us B and A. With passage of time, there is accumulation of products C and D, and there is also depletion of reactants A and B that is occurring. Now, this leads to a decrease in the rate of forward reaction. So, if as this quantity of reactants is going to go on reducing, this rate of forward reaction will also reduce, because now here the quantity is getting reduced and the increase in the rate of reverse reaction will increase. Eventually, the two reactions occur at the same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D, that is no A and B being present initially, as the equilibrium can be reached from either direction. So, if you go from forward direction or backward direction, in both the cases the equilibrium can attain. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by the Haber's process. Now, in this series of experiment, Haber started with a known amount of dinitrogen. Okay, so Haber, what he did, he took a known quantity of dihydrogen, that is N2, and he along with that took H2. He maintained at high temperature and pressure at a regular intervals determined the amount of ammonia that was being present. He was now successful in determining also the concentration of the unreacted dihydrogen and nitrogen. So, if we take nitrogen N2 plus H2, it will eventually give us ammonia, okay, NH3. So, what he was doing, he was trying to figure out that how much is being formed, like how much of NH3 is being formed. Along with that, he was also successful in determining how much of N2 and how much of H2 is still left. Shows that a certain time the composition of the mixture, it remains the same even though some of the reactants are still present. Even though now there is some amount of N2 and H2 that is present, yet you will see that the reaction has stopped. Okay, it is no more further giving the formation of any products. This is happening because this quantity may not be sufficient to form ammonia. Now, in order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting conditions of partial pressure and temperature, but using deuterium in place of H2. So, now just to understand how the dynamic nature of this reaction exists, they did a synthesis of ammonia with same quantity, but instead of taking they started with using deuterium. Instead of taking nitrogen, they started with deuterium, that is D2 and hydrogen. The reaction mixture starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium was attained, these two mixtures, that is H2N2 NH3 and D2N2 ND3, are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the reaction of ammonia is just the same as before. However, when the reaction is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia and dihydrogen and its deuterated forms are present. Thus, one can conclude that scrapping of hydrogen and deuterium atoms in the molecules must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would be no mixing of isotopes in this way. So what happened was, they, after the formation of all of this, they mixed both of this. If now further, if this reaction was supposed to stop there and there, more of this HD and NH2D wouldn't have been forming, but it was forming, indicating that there was some reaction that had not stopped even after they reached the equilibrium. So use of isotope in the formation of ammonia clearly indicates that the chemical reaction reaches a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal, and therefore there is no overall net change that occurs in the composition. Equilibrium can be attained from both the sides, whether we start a reaction by taking H2 and N2 and get NH3, or by taking NH3 which decomposes to give us N2 and H2. Similarly, let us consider this reaction of H2 and I2. Okay, so we get hydrogen iodide. If we initially start with H2 and I2, we will get hydrogen iodide. If we start by taking hydrogen iodide as the reactant, it will decompose to give us back the hydrogen and I2. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.